Assalamu alaikum. So in the last lecture we saw how to compute a first degree polynomial approximation to f of x equal to e to the x at c equals 0. Now if you want to have a better approximation than that, what could we do? We could put more higher degree terms in the polynomial, but then if you have higher degree terms, like for example, let's do this example, find third degree polynomial. So let's call it p3 of x. Its general form will look like a0 plus a1x plus a2x squared plus a3x cubed, where a0, a1, a2, a3 are constants that we have to determine. But to determine these constants, then we need extra pieces of information to pin down these constants. So what we're going to do is, earlier what we did was we required that the value at c that equals the value at c of the original function, the derivative of p at c equals the derivative of the original function. What we're going to do to have more accuracy or to close better approximation, we're going to require the second derivatives equal, the third derivatives are equal in this case. So let's go ahead and write these conditions. So we want the f of 0 equal p3 of 0, f prime of 0 equal p3 prime of 0, f double prime, the second derivative, equals the second derivative of p3, and finally the third derivative equals the third derivative of this at 0. Now, for this particular example, f of x equal e to the x, the higher derivatives are easy to compute. We get derivative of e to the x and e to the x, so every higher derivative is e to the x. Plug them at 0, you get 1. Let's over here on the side write down the higher derivatives of p3. So p3 first derivative is a0 vanishes, you have a1 plus 2a2x plus 3a3x squared. And the second derivative is to differentiate this, a1 vanishes, you have 2a2 plus 6a3x, and finally the third derivative, this is a constant, goes away, and we get 6a3. Okay. So let's plug these in, and so what do we get? From here, we get p3 of 0. If I plug 0 here, I get just a naught. So and this is 1. All of these equal 1, because e to the x plugged at 0 gets 1. So you get from here a naught equals 1. From here you get, if I plug 0 into the first derivative, I will only get a1. a1 also equals 1, because all of these are 1. From here, what do I get? Second derivative, plug 0 into the x, I get 2a2. 2a2 equals 1. And the last one would be 6a3 equals 1. Let's erase this thing to make some space. Putting all this information together, our polynomial will be, you have the constant term is 1, the linear term, the coefficient is 1, a2 is a half from this equality, so you have half x squared plus, and a3 is 1/6. Now this 1/6, how did it come about, is actually 3 times 2, right? When we took the 2 successive derivatives. So it's times 1, it's actually 3 factorial. And the 2 can also be 2 factorial. It doesn't change, the 2 factorial is 2. But I'm doing this for a reason, so that you can begin to see the general pattern. Okay, let's erase this. and see did it give us a better approximate. So what you could do is in your graphic calculator, or you could go to the Alpha search engine tool online and plot these functions, or mathword.com, and you could plot this in e to the x. So earlier we had this was e to the x, and let's take some blue chalk. We had that linear function, right? And it was this kind of approximate, the 1 plus x. It was the first degree polynomial approximation. This cubic term looks something like this. This cubic polynomial. So it's a better approximation in the sense that the deviation from the original function is less. Let's say in this range, it's closer to it. Even out here, it's closer to it. But of course, at some point, even though it will be still closer than that, but still it will be so much far from e to the x that it's not going to be worth it as an approximation. So the general thing here to gather from here is the more terms you add, the more higher derivatives you insist on being equal to the original function, the better an approximation you get. For this particular example, e to the x, let's write down the general nth degree polynomial that will come out of it. You can kind of guess how it would look like. The nth degree polynomial approximation to e to the x centered at c equals 0 is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the n over n factorial. Okay? And this is approximately e to the x at x near c equals 0. Okay? These factorials come about because when you keep taking repeated derivatives of this polynomial, when you have x to the 4 term, you take one derivative, you get 4x cubed, take another derivative, you get 4 times 3 times x squared, and so on until you get 4 factorial as the constant. So from that you can see the general form looks something like this. Having done this example, now we are ready to define such a procedure for functions in general, and we will do this in the next lecture.